All right, I just wanted to take time to show you an example of one of these chemostat problems worked out. And this is, you can think of this as an optional video. So if you feel ready to just dig in and try things on your own, you can just skip this video, that's fine, and go try the web work. You'll get plenty of chances to try this stuff. Otherwise, you're welcome to watch this and watch me try to do this problem. Okay, so how about instead of reading over the problem, I'll just say pause the video and read it. It's from your textbook from page 34, and here it is. Okay, now I'm assuming you're done reading it. All right, so we've got this pond, this volume 100 meters cubed of water, and it's initially pure water. And we've got this this green sludge represents the contaminated water, and it's flowing in, or it's being pumped into the pond, and the fluid flow rate is 0.5 meters cubed per minute. So all of these things are sort of setting the units for the problem. If they're right, like this sets the units of time, little t, in the problem to be minutes. And if you see different units of time showing up in the problem in different areas, then you should like convert everything and make them all the same units. All right, so there's our fluid flow rate, and what else? The concentration of the contaminant in this green sludge is, I think I was calling this C in, is this many kilograms per meter cubed. And contents are well mixed. So this well mixed, this is that assumption I was telling you about, perfectly stirred. This is saying, like, yeah, wherever point in the lake it's getting pumped into, it will probably be more concentrated there, and then less concentrated nearby, and then not so concentrated far away. That's the reality, right? Until you let enough time pass that it gets mixed in and diffuses everywhere. But we're making the assumption, this well-mixed assumption, we're making the assumption that, no, it's just whatever goes in gets spread out perfectly and is instantly stirred perfectly. Okay, so that means it makes sense to talk about a concentration, C of t, of kilograms per meter cubed. I'm just choosing the units based on other units that were chosen for me. This is going to be concentration of chemical in the pond at time t, where t is in minutes. Okay, what else? And they're pumped out at the same flow rate. Okay, good. So 0.5 meters cubed per minute. And my goal is to to find a formula for what is C of t. And to find the equilibrium concentration. So let's get back to equilibrium concentration. Well, yeah, maybe I'll start with equilibrium concentration. So let's write down the differential equation, and I'll show you what is meant by equilibrium concentration. So d dt of the amount of toxic chemical in there, that's C times V, equals the rate at which the chemical enters, that's the fluid flow rate, how many meters cubed enter per minute, times C in, the number of kilograms per cubic meter, minus QC. That's the rate at which the chemical leaves. So Q, I didn't define Q. Q is this number, 0.5 here. Okay, so there's my differential equation, and that's just C prime, write like this, V C prime equals Q times Cn minus C. Maybe that's a nicer way of looking at it. And I'm being lazy and not saying what depends on time, but remember, it's the C is what depends on time. Everything else, this is a constant in this setup. Okay, equilibrium concentration. So I think I never actually mentioned this in lecture. Somehow it slipped lecture. But when you have a differential equation, an equilibrium solution is just a constant solution. So it would be a solution that has the form like C of t equals, and then some constant, like, I don't know what to call it, C naught. Some constant concentration where if that were the concentration, then it would remain that concentration forever. So solutions so that when you plot them, C against t, you just see a straight horizontal line. That kind of a solution. Okay, so if this is to be a solution, then the differential equation holds when I substitute this in, right? So let's impose the differential equation. The left side would be V times C prime. What's the derivative of this? Is 0, because it's a constant. So I have 0 equals, and then the right-hand side of the differential equation would be Q times Cn minus C naught. So Q, Cn minus, and then C is C naught, this constant. Okay, so that means either Q equals 0 or C naught must equal Cn. Q is certainly not 0, Q is 0.5, so C naught must equal Cn. Alright, so the only equilibrium solution, the only constant solution, so the only possible concentration in the lake, where if the lake had that concentration it would stay like that forever, is for the concentration to be exactly whatever Cn is, meaning this 0.0002 kilograms per meter cubed. That makes sense, right? If the lake started out having the same concentration, if it started out being as green and sludgy as what was coming in, then yeah, the concentration is not going to change in time if you just pump in this sludge that has the same amount of toxin in it and pump out the sludge with the same amount of toxin. All right, so that's our only equilibrium solution that we found. Now let's answer the other part of the question. So back here. So determine the equilibrium concentration. And it's, oh, we already did that. Find a formula for the concentration. Now this comment about stability, let's leave that behind. Let's not do that for now. We'll actually learn about that later in the course, a little bit later, not too long, probably next week. So forget about stability for now. Soon. Let's work on finding a formula for the concentration. So now I'm going to focus on this. Okay, now let's see if I can zoom out and try to leave all this stuff visible somehow while I'm working. I don't know if that's so easy to see. How about this? How about I do this and work down here? Okay, so from that other slide, I already knew that C, what was it? C prime times V equals Q Cn minus Q C. That was our differential equation that we got from demanding that the amount of chemical be conserved. Now, to solve, I guess I will use separation of variables, because when I write this, like maybe this is a nice way of writing it. When I write it like this, I see that I've got C prime equals, and then something involving only C. And there's no time here. There's not even little t. But even if there were little t, that wouldn't necessarily be a problem. Like if it's, as long as it's, how do I put this? Basically this is separable. For it to be separable, I need the right-hand side to be some, I need the right-hand side here to be some function g of c times some function h of little t. And I have that. In fact, I have just this nice function of c. So it is separable. In fact, it's already separated. So all I need to do now is divide both sides by this thing. And like before, I'm just going to divide by this thing because I don't want to have my integral be more complicated looking than necessary. So this is dc dt. So let me just write it as dc. And then move the dt over to the other side. How about like that? And then suddenly I'm going to start viewing this as an integral. And, you know, I can do indefinite integrals and do the plus c and get my general solution. But in the end, I want a particular solution, right? I want to find a formula for the concentration. So instead of finding a general solution and then solving for the free parameter by imposing the initial condition, I can put in the initial condition right now. What's the initial condition? Here. The water is initially pure. So let's write that as an equation. Initially pure water, that is just another way of saying that C at time 0, let's say 0 means initially, so that time is now being measured from, since the water was pure. So time is minutes elapsed since the water was pure. And we're being told that C of 0 here is 0. Pure water means the concentration of chemical in it is 0. Okay, so that's our initial condition. C of 0 is 0. Now, I can actually like put that right in here by making these definite integrals. And then I don't have to deal with the plus c that comes out of the integration. So as time runs from 0 to some time t, and okay, I shouldn't confuse the variable of integration with this thing. It's not going to be very important anyway. But as time runs from 0 to time t, concentration, capital C, runs from value 0. So this 0 is this 0 here. This 0 is this 0 here. Concentration runs from 0 to whatever is C of t. And, you know, I'd rather just be a little bit sloppy here and leave this as little t. And hopefully you're aware that these are different things. Okay. So now on the left side, I've got log of C minus Cn, evaluated from 0 to C of t. And on the right side, I've got, this is just a constant, so that times t, evaluated from 0 to t. So on the left side, I've got log C of t minus Cn minus log of minus Cn. And Cn is positive, so I have done something wrong. Now I have a log of a negative number. All right, let me pause and see what I did wrong and come back. Okay, I'm back. So this is an interesting problem. And it is definitely something we should be paying attention to. So when I integrate this, the integral is really the log of the absolute value, right? It's not the log, but it's the log of the, it's not the log of this, but the log of the absolute value. That means if it were negative, then you need to force it to be positive by flipping the sign. Now, actually, it's quite annoying, and I find confusing to deal with that absolute value. So usually, I get around it by ensuring that whatever I'm taking the log of is positive when I do this. So I find it easier to go back and make sure that what I've got is positive. Now, c minus c in, typically I actually do expect that to be negative. So if I'm going to integrate and get a log of absolute value, there's a minus sign that needs to be here. So it should really say log of c in minus c. So the reason I say that c minus c in I expect to be negative, because concentration in the lake starts out 0, and it's going to be 0 minus this thing. C minus c in is going to be 0 minus this positive number. So c minus c in starts out negative. At time 0, it's negative. And then it's going to become less and less negative as time goes on and the concentration in the lake increases. Okay, so I expect that c minus c in is going to be negative as time goes on. And so I would rather rearrange some things. Let me do this in a color so that you can more clearly see how I'm rearranging things. I'm actually glad this happened because you don't want to see me doing everything perfectly. You want to see the problems that can arise, because those are things that can happen to you when you're working this stuff out. If you have no fear of the log of absolute value and working with that, then go for it. Personally, I just make mistakes with that. So let's see. Over here, let me remove the minus sign from here and then flip this around to say c in minus c. Then over here, I can remove that minus sign and flip this around to say c in minus c. And c in minus c really is, now it's positive. C in minus c is going to be positive normally, right? It starts out positive because c starts out at 0, and then it continues to be positive as time goes on. Now here, I can say, when I integrate, I get c in minus c. And that is correct. However, I'm missing something coming from the chain rule. So if you were to differentiate this with respect to c, think about what you get. If you were to compute ddc, if you were to compute ddc of log c in minus c, do you actually get the integrand here? No. You would get 1 over c in minus c times negative 1 from the chain rule, due to the chain rule, due to the fact that there's a minus sign here. So to make this correct, I need a minus sign here. Let me make that blue to indicate that that came out of my corrections. And also I had removed this minus sign. There used to be a minus sign here, and I removed that. So let me erase that from there. Okay, that looks better. Now let me erase the wrong stuff and proceed. So here I get log, negative log c in minus c of t minus log Cn equals, and then Q over V times T minus 0. So just Q over V T. Okay. Q over V T. And then let me rewrite the left-hand side. So that's log Cn over Cn minus C of T. So that looks pretty good. And now exponentiate both sides. We get Cn over Cn minus C of T equals e to the Q over V, which is just some constant, times T. And there's no plus C that I added anywhere. I didn't really need the plus C because these are definite integrals. So I've baked in the initial condition that we start with pure water. I've baked that into the way I did the integral. The fact that I have time starting at 0 and concentration starting at 0 when I'm doing this integration over T and over C. So this already satisfies the initial condition, and now I'm just trying to solve for C of T. Okay, now it's going to be some algebra from here. So I think this part is a little bit boring. You might speed it up or skip ahead, but I'll do it. E to the Q over V T. The goal is to solve for C of T here. So Cn equals Cn e to the Q over Vt minus C of T e to the Q over Vt. So let me do this kind of in one step. So adding this term to the other side, I get that, and so C of T is the, well, let me move this minus sign to the other side and divide by e to the Q over Vt. So minus Cn 1 plus e to the Q over Vt all over e to the Q over Vt. And there's certainly a nicer way to write that. It's minus Cn yeah, e to the minus Q over Vt plus Cn. Does that look right? I think so. Okay, cool. So that, I think that is my answer. And I haven't put in any numbers yet. The numbers are way back up here. You know, the value for Cn and the value for Q. But how about we plot this in Mathematica and just look at what it looks like? How does the concentration of chemical in the lake change in time? So I'll be right back. Okay, so here's my Mathematica. I'm just going to define what the constants are so I don't have to type in specific numbers repeatedly. So Cn is going to be 0.0002. And Q will be 0.5 from here, and V will be 100. That was over here. And I think those are all the constants. Then let me go back. Here's my solution. And let me go ahead and try to plot that. So first I'll define the function. And this underscore notation is part of how you define functions in Mathematica. So, and I'm not going to call the function capital C because for some reason that name is taken for something else. So minus Cn exponential of minus q over v t plus Cn. Okay, so that's good. Now I can evaluate concentrations at various times. So for example, I can check quickly that my initial condition holds. C of 0 is 0. Good. I can check, okay, what's the concentration in the lake at time 1? It's whatever is that number, which is very small, 10 to the minus 7. What about at time 100? Looks like it's bigger. That makes sense. The concentration is growing. And yeah, of course you can see that the concentration is growing because it's Cn plus or minus this thing, and this thing is shrinking as time goes on. It's decaying. This would be exponential decay. So I've got, so C of t is Cn minus something that's decaying. And finally, the actually interesting part. Oh, well, no, before we do that, let's verify that it satisfies the differential equation. So this is a really good way to check your work. Let's go, this was the differential equation, right? C prime v equals this stuff. So let's check. C prime of t times v is whatever that number is. That's the left-hand side of this differential equation, and then the right-hand side is q Cn minus q C of t. Okay, and I've learned that I should simplify when I'm doing this check. So that looks not so simplified. Aha! Good, they look the same. Another thing I could do instead of this is to look at the equality. So put two equal signs like that. Look at this equality and then simplify the equality statement. And when I evaluate that, I get true. So the equality simplifies to true, meaning it is a true equality. So the differential equation holds. Great, so that means I did it right. And I'm personally a little bit surprised that there were no mistakes, except for that one weird thing with the log of a negative. So I'm feeling pretty good about this. And now let me plot C of t with t running from, let's say, 0, which is when it's pure water. So when C is 0, let's run it out to like 100 or something. Oh, interesting. Let's run it for longer. Ah, more interesting. How about for longer? For 10,000 minutes. Okay. Let me stick with 1,000 minutes. Yeah, you can kind of see that. I don't know if this is visible in the video. I hope it is. I can increase the magnification. You can see that the concentration, so the vertical axis concentration, horizontal is time in minutes. So we start at pure water, and then the concentration of chemical increases, but it's approaching something, right? It's approaching 0.0002. That was our equilibrium solution from before. So it's approaching the equilibrium concentration. Hopefully that makes some intuitive sense that it would behave that way.